Upon completion of this topic, you will be able to recognize the normal operation of the corporate Caterpillar starting system. When you have completed this segment, you will be able to identify and state the function of the components of the corporate Caterpillar starting system. Every Caterpillar machine that is powered by a diesel or spark-ignited engine has a starting system to crank the machine's engine. Starting systems of the type described here convert electrical energy from the battery into mechanical energy at the starting motor. If a problem develops in the starting system, the operator needs a service technician right away. Let's take a closer look at the components of the Caterpillar starting system. The battery disconnect switch removes all electrical circuits, including the starting circuit, from the battery negative terminal. When this switch is off, there is no power to any circuit in the machine. The two 12-volt batteries in series power the starting motor and establish a nominal system voltage of 24 volts. The circuit breaker limits the amount of current allowed to flow through the circuit. This protects the wires and components of the circuit in the event of a short to ground. The key start switch enables the operator to start the engine by way of the start relay. The start relay permits the relatively small current flowing through the key start switch and start relay coil to control the moderate current needed to activate the starter solenoid. The relay also affords the shortest possible path for the current to the starter solenoid. The starter solenoid, in turn, permits the moderate current flowing through it to control the heavy current needed to drive the starting motor. The starter solenoid first engages the starter motor pinion gear with the engine's flywheel. Once the pinion gear is engaged, it allows current to flow through the starter motor. The starter motor cranks the engine at a speed sufficient to allow the engine to start. The connector provides the necessary connection between harnesses and components. The wiring harnesses connect the various electrical components. This technician is using a schematic diagram to trace the starting circuit. He is identifying each of the components in the machine by locating its symbol in the schematic. In this module, we will use a simplified starting circuit schematic to explore circuit faults and practice troubleshooting skills. Here is the simplified starting circuit. Like the components you just saw, the components in this model's starting circuit perform the following functions. 1. The battery disconnect switch allows you to manually disconnect the batteries from all machine circuits when no power is required. In the off position, all circuits are open and cannot draw current from the battery. 2. Two 12-volt batteries connected in series establish a nominal system voltage of 24 volts and supply current to the circuits. Parallel electrical paths are provided to the key start switch, the start relay, and the starter. The starting circuit places high demands on the batteries when cranking the engine. 3. A circuit breaker limits the amount of current allowed to flow through the starter motor control circuits. This protects the harness and other components in case of a short circuit. 4. The key start switch is a manual switch capable of activating two circuits at one time. When turned to the middle or on position, the switch activates the main power circuit. When switched to the far or start position, the switch also allows current to flow through the start relay coil. 5. When activated by current flowing through the start relay coil, the start relay contacts close and allow current to flow through the coils of the starter solenoid. 6. The starter solenoid is mounted on the starter motor. Together they make up the starter assembly. The solenoid first engages the starter motor pinion gear with the engine's flywheel, then permits current to flow through the starter motor to crank the engine. The starter motor is a powerful electric motor whose only function is to crank the engine. It requires high current in order to develop the power needed to bring the engine up to starting speed. The motor shares a ground connection with the starter solenoid. 7. A connector completes the circuit between the key start switch in the operator's compartment and the start relay and circuit breaker in the engine compartment. Connectors are typically used between the cab and engine areas to facilitate factory assembly as well as service in the field. 8. The wiring harnesses route and conduct electricity to the circuit's components. The Caterpillar battery disconnect switch facilitates electrical system troubleshooting and servicing by providing a convenient disconnect point. Secures the machine and all electrical systems from unauthorized operation. The Caterpillar battery disconnect switch eliminates slow battery discharge caused by electrical equipment. When a machine is to be stored more than 1 month, the disconnect switch should be opened. Is a quick and convenient method of disabling the machine's electrical system in the event of some types of system failures. Caterpillar maintenance-free batteries provide greatly extended maintenance intervals, 1,000 hours. The original lead-acid batteries were 100 hours. High cold cranking amperage, CCA, and reserve capacity ratings. Sealed cover to prevent contamination and increase case strength. Lightweight polypropylene case for high impact resistance. Caterpillar maintenance-free batteries provide PVC or polyethylene separators for better vibration resistance and more protection against interplate shorts than paper separators. Plates anchored at their base to the battery for better vibration resistance. The Caterpillar circuit breaker protects wiring from damage due to excessive current, minimizing downtime and service costs. Tolerates high transient currents associated with electrical motor startup. Eliminates the need for fuse replacement and possible error. Increases power system reliability and decreases complexity. The Caterpillar circuit breaker returns a machine to productive operation more quickly than fuses using the resettable feature. Reduces the possibility of changing the overcurrent protection value as happens when a fuse is replaced with a fuse having an incorrect rating. The Caterpillar key start switch is used to control a start relay for convenient key starting. Discourages unauthorized machine operation. Has a control terminal that is on when the key switch is off. This is used by some electronic controls which need to know the key switch position status. The Caterpillar key start switch provides a convenient operator engine off on machines equipped with electronic engine shutdown, fire suppression systems, or electronic unit injection, EUI. The Caterpillar start relay provides for easy, convenient key starting. Extended service life of the key start switch by using low current to energize the relay coil in order to control moderate current required for the starter solenoid. Easier troubleshooting and servicing through common design. The Caterpillar starter motor and solenoid are sized to provide enough engine speed to start the engine even at temperature extremes. Of a heavy-duty design to survive the work environment encountered by heavy equipment. Typically grounded with a separate ground stud and cable rather than a case ground to ensure a good ground connection. Caterpillar connectors provide for quick troubleshooting and servicing of the electrical system by providing convenient disconnect points. Easier, more logical machine assembly procedures. Protection of connector pins and sockets from mud, oil, and other contamination. The selection of wire gauge according to the rating of the associated fuse or circuit breaker, which prevents an overcurrent from destroying a wire or insulation before the fuse blows or breaker trips, is one of the benefits of Caterpillar wiring harnesses. They also provide the benefit of nylon braid, which protects wires from abrasion, reducing the chance for shorts. Braid and insulation are resistant to all engine and vehicle fluids over the entire range of operating temperatures. Caterpillar wiring harnesses provide these benefits. Harness wear points are reduced by well-designed harness routing and effective use of chain link, tie wrap, and bolt-on clips for general routing and steel conduit for battery cable routing. They help to make servicing and troubleshooting faster and easier. Circuit numbers hot-stamped on wire insulation, combined with wire color, relate each harness wire to the electrical schematic. When you have completed this segment, you will be able to recognize normal current flow in the corporate Caterpillar starting circuit with the switch on. Recognize the normal operation of the corporate Caterpillar starting system as indicated by its sounds. Recognize normal current flow in the corporate Caterpillar starting circuit as represented on the DMM and clamp-on ammeter simultaneously. This is a Caterpillar starting circuit. The components of this circuit are 1. Battery disconnect switch, 2. Batteries, 3. Circuit breaker, 4. Key start switch, 5. Start relay, 6. Starter, 7. Connector, 8. Wiring harness. This section explains how the starting system components normally work together to crank the engine. With the key start switch in the off position, no current can flow in the circuit. When the key start switch is in the on position, it provides power to other electrical systems in the machine not shown here. But this does not cause the engine to start. Starting occurs when the key start switch is placed in the start position. First, current flows from the batteries through the start relay coil and back to the batteries. The current through the start relay coil produces a magnetic field which attracts the relay armature, closing the relay contacts. Current can then flow from the batteries through the starter solenoid coils and back to the batteries. The instant the start relay closes, voltage is applied to both coils at test point 8. About 46 amperes now flow through the starter solenoid coils. Some 6 amperes flow through the hold-in coil directly to ground. About 40 amperes flow through the pull-in coil to ground through the starter motor winding. These currents produce a magnetic field around the starter solenoid which moves the starter pinion into engagement with the engine flywheel, and at the same time closes the starter solenoid contacts. This connects the starter directly to the batteries and the battery voltage on both ends of the pull-in coil. Current continues to flow through the hold-in coils to sustain the magnetic field and keep the contacts closed during cranking. Now current can flow from the batteries through the starter motor and engine cranking begins. Cranking continues until power to the starter assembly is removed by returning the start switch to the on position. Through this sequence of actions, this starting circuit permits a current of about 1 ampere flowing through the key start switch to control a cranking current of 400 to 1200 amperes through the starter motor. This is the normal flow of current in the starting circuit during engine cranking. Notice that this starting circuit is actually a series parallel circuit with 4 current paths. Each current path, or circuit, begins at battery pos, test point 1, and returns to battery neg, test point 14. Can you trace them? Test points 1, 2, 3, 4, 5, G, 12, 13, and 14 make up one of the circuits. Test points 1, 6, 7, 8, 11, 9, G, 12, 13, and 14 form a second circuit. Test points 1, 6, 7, 8, 9, G, 12, 13, and 14 form a third circuit. Test points 1, 10, 11, 9, G, 12, 13, and 14 form a fourth circuit. When the key start switch is placed in the start position, the start relay closes with a click that can be heard if not drowned out by other noise. The starter solenoid makes its own distinctive sound as the starter motor pinion engages the flywheel and the solenoid contacts close. If the engine starts normally, you may not hear these sounds over the noise of the engine. But watch and listen now as we slow down the action so that you can hear them. During normal operation, you can hear the engine cranking and starting, but you may not be able to hear the clicks of the start relay and starter solenoid engaging. These sounds are usually drowned out by engine noise. Even under abnormal conditions, when the engine does not crank, you may not be able to distinguish the click of the start relay from that of the starter solenoid. If you are able to hear the click of the start relay during abnormal operation, it is because it is positioned close to the key start switch. However, this is not the case on all machines. In addition to using sounds, you can also check for normal current flow using the DMM and clamp-on ammeter. This lets you confirm that components and connections are not causing excessive voltage drop. The batteries are within specifications. During cranking or while attempting to crank, the voltage across the battery posts will vary depending on ambient temperature, engine oil viscosity, battery condition, condition of the cables and connections, and finally the mechanical condition of the engine. The voltage during cranking should read from 16 to 20 volts for a 24-volt system at 27 degrees centigrade, 80 degrees Fahrenheit. Cranking voltage varies considerably with ambient temperature due to reduced battery capacity at colder temperatures. Use this chart to interpret system voltage readings during cranking. During cranking or while attempting to crank, the voltage drops across the switches, contacts, cables, wiring, and connections in the circuit must not exceed the maximum allowed. In circuits that draw this much current, even a little resistance can result in a significant power loss. These are the maximum allowable voltage drops in a 24-volt starting circuit during cranking or while attempting to crank. The maximum allowable voltage drops for 12-volt starting systems are exactly half the voltage drops shown here. During cranking or while attempting to crank, you can use the clamp-on ammeter to measure the current between the battery positive terminal and the starter motor. The maximum allowable current draw for a 24-volt starting system is about 750 amperes. The exact value depending on engine size and starter rating. The maximum allowable current for a 12-volt starting system is about 1200 amperes. Upon completion of this topic, you will be able to analyze the corporate Caterpillar starting circuit to the fault identification level. When you have completed this segment, you will be able to identify sounds that are symptoms of abnormal operation in the starting system. Recognize the relationship between abnormal starting system sounds and starting system components. Identify the three basic electrical faults in a typical Caterpillar starting system. Trace the flow of current through the starting circuit with each of the three basic faults, one at a time. Recognize the effect of an open, short, and short to ground in a typical Caterpillar starting circuit as represented by readings on the DMM and clamp-on ammeter. Predict changes in behavior and DMM clamp-on ammeter readings as a result of opens, shorts, and shorts to ground in the circuit under test. Interpret changes in DMM clamp-on ammeter readings as a result of open, short, and short to ground in the circuit under test. While attempting to crank the engine, you may hear certain sounds that tell you there may be a problem with the starting circuit. Sounds that tell you there may be a problem with the starting circuit. No sound at all with the key in the start position. No sound at all is heard when the key start switch is turned to the start position. This sound may indicate that the start relay coil is bad. The start relay is not getting power. Possible causes of the start relay not getting power: the batteries are dead or very low. There is an open circuit caused by open battery disconnect switch, open circuit breaker, battery cable removed from post, connector disconnected, faulty key start switch. Sounds that tell you there may be a problem with the starting circuit: the start relay clicks with the key in the start position. No other sound. The start relay clicks with the key in the start position, but no other sound is heard. This sound indicates a problem in one of the following areas: start relay contacts, starter solenoid, starter motor, wiring and connections, batteries, low state of charge, pinion to ring gear butt engagement, engine or transmission locked up. Sounds that tell you there may be a problem with the starting circuit: a chatter or repeated clicking sound with the key in the start position. A repeated clicking noise or chatter with the key in the start position. This sound indicates the starter solenoid is getting current, but there may be an open starter solenoid hold-in coil, low voltage at the starter due to low battery charge, high resistance in the circuit, poor contacts or connections. Sounds that tell you there may be a problem with the starting circuit: the engine cranking slowly and sluggishly. The engine cranks slowly or sluggishly. This suggests that the problem may be the starter motor, bad brushes or armature, partly shorted windings, mechanically binding, low voltage to the starter motor, partly discharged batteries, high resistance in circuit. A mechanical problem in the engine causing excessive drag. A combination of high viscosity motor oil and cold temperature. Sounds that tell you there may be a problem with the starting circuit: a grinding or clashing sound between the starter pinion gear teeth and ring gear teeth while attempting to crank the engine. A grinding or clashing sound between the starter pinion gear and the engine ring gear teeth. This sound might indicate the incorrect part, possibly the pinion, being installed. A misadjusted pinion clearance causing partial engagement of the pinion with the ring gear. A loose starter mounting or badly worn pinion or ring gear. Here again are the sounds that suggest a problem with the starting circuit. Some point to a specific component, while others have more than one possible cause. No sound at all with the key in the start position. The start relay clicks with the key in the start position, but no other sound. A chatter or repeated clicking sound with the key in the start position. The engine cranking slowly or sluggishly. A grinding or clashing sound between the starter pinion gear teeth and ring gear while attempting to crank the engine. Problems in Caterpillar starting systems may be caused by an unintended open, series resistance, short, or short to ground in the circuit. The effects of these faults can be demonstrated on the same sample starting circuit already used to describe normal operation. In this example, there is an open in the start relay coil. As a result, current stops flowing in all parts of the circuit. Without current, the start relay and starter solenoid cannot close and the starter motor cannot operate. Therefore, the system makes no sound at all with the key in the start position. With the start relay closed, The voltage between test points 7 and 9, ground, while cranking should be about 16 to 20 volts. With the start relay coil open, the voltage between these 2 points should be 0 volts, as the open relay contacts would isolate the solenoid coils from system voltage. Here, an open has occurred in the starter motor circuit wiring just to the right of test point 10. With this fault, there would be an audible click from the start relay and the starter solenoid when the key start switch is placed in the start position, but the engine would not crank. In this circuit, a resistance fault has occurred in the connector due to corrosion. As battery voltage drops during cranking, the fault reduces the current in the wire to the start relay coil to the point that the coil can no longer hold in the contacts. When they open, the solenoid coil loses power, the solenoid contacts open, and the starter motor stops cranking the engine. A resistance of 72 ohms between a pin and a socket in the connector reduces current flow through the start relay coil from the normal 1.0 ampere down to 0.25 ampere. It also drops voltage at the coil, test point 5, to 5.0 volts, and the relay coil can no longer hold in the contacts. As a result, the voltage path to the solenoid coils is opened, and the solenoid contacts open. Another example, a resistance fault occurs between test point 9, the starter ground stud, and ground, causing the engine to crank more slowly than normal. This is a common problem which can be caused by corrosion, a loose connection at one or more locations, or physical damage. Increased resistance here can slow down or altogether prevent cranking. A short in this circuit is creating an unintended current path through the start relay contacts. This allows current to flow to the solenoid hold-in coil, even though the start relay coil is de-energized. As a result, the starting motor continues to operate whether the key start switch is in the off or on position. Normally, when the key start switch opens, the start relay contacts also open because there is no current through the start relay coil. You would then expect to see a DMM reading between test points 6 and 7 of 25.2 volts. In this case, because the start relay contacts are shorted, the reading is 0.43 volts. In this circuit, the start relay coil is shorted. The key start switch is in the start position, but the start relay contacts cannot close because the start relay coil no longer has the necessary magnetic pull. The short also creates a path for current back to the battery, which trips the circuit breaker and disables the starting circuit. In this circuit, an unintended short to ground has occurred between the circuit breaker and the start relay contacts. This fault has caused the circuit breaker to trip, preventing current flow in the entire starting circuit. With the disconnect switch off for resistance tests, the reading from test point 6 to G, ground, should be OL due to the open contacts in the start relay. However, because of the short to ground between the circuit breaker and test point 6, the resistance between test point 6 and ground is nearly 0 ohms. This circuit has a short to ground between the start relay contacts and the starter solenoid. This fault diverts current from the starter solenoid circuit directly back to the batteries. Because of the low resistance of this short to ground, the circuit breaker trips and the start relay contacts open. The starting circuit is now completely disabled. When you have completed this segment, you will recognize the procedure for measuring voltage drop across the battery and current draw from the battery during a crank attempt using the DMM and clamp-on ammeter. Recognize the procedure for measuring starter voltage drop across the starter and current draw through the starter during a crank attempt using the DMM and clamp-on ammeter. Recognize the procedure for checking for engine seizure. Recognize the recommended troubleshooting procedure for the corporate Caterpillar starting system. Testing is an integral part of diagnosing problems in the starting system. When the starter cranks the engine unusually slowly, or not at all, 3 tests are commonly used to isolate the problem. Measure the battery voltage and starter current while cranking or attempting to crank the engine. Measure the voltage drop across the starter while cranking or attempting to crank the engine. Check for engine seizure or other mechanical problems. To prepare the system for the measurement, set the DMM to 200 dCV range. Connect the black test lead to battery neg terminal that leads to ground. Connect the red test lead to battery pos terminal. Install the clamp-on ammeter on cable leading from battery pos terminal to starter BET terminal. Observe the battery voltage and cranking current while cranking or attempting to crank the engine. If the cranking voltage is less than the minimum typical cranking voltage for the system, determine the cause of the low battery voltage. Low batteries can be caused by a battery condition or a shorted starter. Review the chart on the next screen for the minimum typical cranking voltage of 12 and 24 volt systems at various temperatures. Battery capacity decreases as the ambient temperature goes down. Notice that the minimum typical cranking voltage for a 24 volt system at 16 degrees centigrade, 60 degrees Fahrenheit, is 15 volts, and at negative 12 degrees centigrade, 10 degrees Fahrenheit, it is 13 volts. If the cranking current exceeds the maximum rated starting cranking current, discontinue the test and determine the cause. Typical maximum currents are 750 amperes for a 24 volt system and 1200 to 1400 amperes for a 12 volt system. If cranking voltage and current are normal, perform test 2. Prepare the system for the measurement. Set the DMM to 200 dCV. Connect the red test lead to starter solenoid bat stud, not on cable terminal. Connect the black test lead to starter motor ground stud, not on cable terminal. Observe the voltage drop across the starter while cranking or attempting to crank the engine. If the voltage drop is more than 2 volts below the battery cranking voltage determined in test 1, look for an excessive voltage drop between the batteries and the starter. Review the chart on the following screen for the maximum allowable voltage drop across other components of the starting system. Voltage drops greater than those shown here are usually caused by loose or corroded connections or defective switch contacts. The maximum allowable voltage drop while cranking the engine from battery neg post to starter neg post is 1.4 volts in a 24 volt system and 0.7 volts in a 12 volt system. The maximum allowable voltage drop while cranking the engine across the disconnect switch is 1.0 volts in a 24 volt system and 0.5 volts in a 12 volt system. The maximum allowable voltage drop while cranking the engine across the starter solenoid contacts is 0.8 volts in a 24 volt system and 0.4 volts in a 12 volt system. If the battery voltage and starter and cable connection voltage drops are within specifications, but the engine will not crank using the starter, check for mechanical problems that could prevent the crankshaft from turning by performing test 3. Using an engine turning tool, attempt to rotate the crankshaft manually. If the crankshaft is abnormally hard to turn or cannot be turned at all, the engine has a piston seizure or other mechanical problem which must be repaired. If the crankshaft turns freely by hand but still cranks sluggishly with the starter, replace the starter. In this segment, you will troubleshoot 3 separate starting circuit problems. Questions and instructions will guide you as you work through the problems. Each of the following exercises begins with the description of a problem one of your customers is having with the starting circuit on a Caterpillar machine. The exercises in this topic guide you through the troubleshooting process. For this reason, you will only be able to operate a component of the circuit or take a measurement in this topic when asked. In some steps, you will be asked to open or close a switch or the connector. When you are asked, the appropriate symbol is active, and you will be able to open or close the switch or the connector by selecting the schematic symbol for that component. In other steps of these exercises, you will be asked to use the DMM or the clamp-on ammeter to make a measurement. When you are asked, the appropriate symbol is active, and you will be able to operate the DMM or the clamp-on ammeter by selecting it. Use your knowledge of electricity and your understanding of the Caterpillar starting system to follow the logic of how these problems are being solved. You are now ready to begin the guided troubleshooting practice exercises for the Caterpillar starting circuit. Upon completion of this topic, you will be able to recognize the normal operation of the corporate Caterpillar charging system. When you complete this segment, you will be able to identify and state the function of the components of the corporate Caterpillar charging circuit. Every Caterpillar machine with an engine starting system also has a charging system. The charging system has 2 functions: to recharge the batteries used to crank the engine, and to supply current to all electrical systems during machine operation. Next, we will look at the components of a typical Caterpillar charging system. The alternator is the key component of the system. It converts rotating mechanical energy from the engine into electrical power to charge the batteries and operate electrical devices. An internal voltage regulator within the alternator controls the alternator output. The alternator breaker protects the alternator circuit and the batteries from excessive current flow in the event of a malfunction. A connector is usually installed between the alternator breaker and the alternator to facilitate servicing. The wiring harness routes electrical power from the alternator to the batteries and all other electrical loads on the machine. The starter assembly is not an active component of the charging system. However, it typically provides important battery positive and ground negative connections that are necessary for the alternator to function. 2 12-volt batteries connected in series for 24 volts store the electrical energy produced by the alternator. The battery disconnect switch allows you to manually disconnect the batteries from the circuit when no power is required. When this switch is in the off position, the charging system cannot charge the batteries, and the batteries are protected against unintended discharge. These technicians are using a schematic diagram to trace the charging circuit. In this module, you will use a simplified charging circuit schematic to explore circuit faults and practice troubleshooting skills. Here is a simplified circuit. Like the one you just saw, this model charging system includes the following components. 1. The alternator provides sufficient current for all continuous loads during machine operation and provides battery charging current. The alternator is self-limiting for current. The integral voltage regulator establishes the charging voltage level of the electrical system. The standard level for 1990 and earlier Caterpillar machines is 27.5 volts DC, plus or minus 1 volt. This standard was changed in mid-1991 to 28.0 volts DC, plus or minus 1 volt. 2. The alternator breaker protects the batteries from excessive current draw in the event of a short to ground within the alternator or between the alternator breaker and the alternator. It also protects machine wiring from possible overload in the event someone installed an oversized alternator to furnish power for unauthorized accessories. 3. The connector provides a convenient way to disconnect the alternator from the rest of the circuit, either for troubleshooting or replacement of the alternator. 4. The wiring harnesses and cables distribute power throughout the circuit. 5. The starter assembly, although part of a different system, provides the charging system with important battery connections. 6. The two 12-volt batteries provide power to crank the engine of the machine. 7. The battery disconnect switch disconnects all electrical circuits, including the charging circuit, from the battery negative terminal. When the switch is off, the alternator cannot charge the batteries, and the batteries cannot be discharged by an unintended electrical load or circuit failure on the machine. 8. The engine block serves as a ground for the alternator and sometimes other engine circuits. The engine block is normally connected to the starter ground post by the engine ground cable, which completes the ground path from the alternator back to the machine frame ground and the battery negative post. 9. The engine ground cable is an essential part of the charging circuit. If it is removed, the alternator may still work, but the charging ground path is then through the main bearings of the engine and through transmission and other gears to the machine frame. A missing ground cable is not good for bearing surfaces and often results in bearing or gear failure. 10. The starter ground cable connects the starter ground post and the engine block with the machine frame ground. The Caterpillar alternator has an integral voltage regulator and extremely low battery leakage current during machine off time. Is sized to carry 100% of the machine electrical load for longer battery life and more reliable cranking. Is brushless in some models, minimizing the possibility of connection problems and eliminating brush wear concerns. The Caterpillar alternator breaker is sized according to the alternator output current rating. Protects wire insulation from damage due to a short or short to ground. Includes a thermal overload feature which permits transient currents above the current rating without tripping the breaker. Includes a reset feature to return machines to work more quickly. The Caterpillar connector allows safe, easy troubleshooting and servicing of the electrical system. Permits easy replacement of the alternator without the need to cut and splice wires. Caterpillar wiring is gauge selected with a current rating which exceeds that of the fuse or breaker protecting the wire. Shorts trip the breaker or blow the fuse before the wire burns. Protected against abrasion by nylon braiding. This reduces the chance for shorts. Braiding is resistant to all fluids commonly used in the engine and machine over the expected range of operating temperatures. Caterpillar wiring harnesses reduce harness wire abrasion points, a possible fire source, and control routing by using chain link and tie wrap, general routing, bolt-on clips, general routing, steel conduit, battery cable routing. Caterpillar wiring harnesses help make troubleshooting easier with circuit numbers hot-stamped on wire insulation, which relate each wire in a harness to the numbers on the electrical schematic. Caterpillar circuits use starter cables and ground cables sized according to the current requirements of a particular engine and starter. The engine block as the conductor from the alternator ground wire to the engine ground cable. The Caterpillar starter assembly is sized to provide sufficient engine speed to start the engine at the application's temperature extremes. Designed to withstand operator abuse and system malfunction, for instance, overcranking. Usually grounded via a large ground cable, as opposed to a case ground, to ensure a good ground connection. Caterpillar maintenance-free batteries never need water, provide high cranking power, high reserve capacity, and longer life during out-of-service periods. Are highly resistant to damage from vibration, road shock, or severe temperature changes. Have a heat-sealed cover to prevent contamination and increase strength. Caterpillar maintenance-free batteries use a polypropylene case for lightweight and high-impact strength. Use strong, finer-grained, high-density lead plates with PVC or polyethylene separators for better vibration resistance. Will tolerate a 45-degree tilt without spilling electrolyte, which permits their usage in rough terrain applications. Caterpillar maintenance-free batteries have a centered plate strap and through partition connectors for the shortest electrical path to get maximum starting power. Include a built-in flame arrestor vent to reduce the possibility of explosion caused by an externally produced spark. The Caterpillar battery disconnect switch secures electrical systems and the vehicle from unauthorized operation. Extends battery life. Parasitic or accessory loads can be disconnected during extended non-operation time. Allows complete removal of battery power from the machine. Facilitates safe electrical system troubleshooting and servicing using the convenient disconnect point. When you've completed this segment, you'll be able to describe the normal flow of current in the corporate Caterpillar charging circuit while performing its two functions. Recognize normal current flow in the corporate Caterpillar charging circuit while performing its two functions as represented on the DMM and clamp-on ammeter. Let's review the components of the Caterpillar charging circuit. 1. Alternator. 2. Alternator breaker. 3. Connector. 4. Wiring. 5. Starter. 6. Batteries. 7. Disconnect switch. 8. Engine block. This section explains how the charging system is connected together and how the system normally charges the batteries and supplies power to the machine. The components of the charging circuit are connected in series. Although not obvious, there is an additional parallel ground return path for charging current through the engine main bearings. This path is important to know about for troubleshooting certain faults, as you will see later. When the engine is not running, no current flows in the charging circuit. When the machine is being started, current is supplied by the batteries to crank the engine. Once the engine is started and the alternator begins operating, charging current flows through the batteries. The charging current flows in the opposite direction from the current supplied by the batteries during engine cranking. Now it is the alternator, not the batteries, that handles the system's current delivery requirements. Current flows from the alternator, both to charge the batteries and to supply to all other electrical systems in the machine needing it. The alternator develops direct current, DC, in 3 stages. The alternator develops direct current, DC, in 3 stages. Stage 1. Generation of 3-phase alternating current, AC. Rotation of the alternator shaft generates alternating current, AC. There are 3 sources of AC in the alternator, each producing 1 phase of current. Each phase is 120 degrees, or 1/3 of the full alternation cycle, from the others. Stage 2. Rectification of three-phase alternating current, AC, to pulsating direct current, DC. The three-phase AC goes through a diode assembly within the alternator to convert the three-phase AC to pulsating DC, direct current with a rhythmic variation in the peak voltage. This is accomplished by the diodes in the alternator redirecting the negative pulses of the AC to positive pulses. Stage 3. Regulation of the output voltage to limit it to a preset value. A voltage regulator inside the alternator then limits the output of the alternator to a preset voltage. The rhythmic variation in the voltage is reduced by energy from the batteries, becoming a variation of less than 0.2 volt in a 24-volt system. These are the three stages in the development of direct current, DC, from the AC output of an alternator. 1. Three-phase AC. 2. Pulsating DC. 3. Regulated pulsating DC. When the third stage is reached, it is direct current with a very small remaining pulse. This supplies power to charge the batteries and operate all the electrical systems on the machine. The voltage regulator maintains system voltage level by varying the duty cycle of the field current in the alternator. A high ratio of on time to off time increases output voltage. A low ratio of on time to off time decreases output voltage. You can check for normal operation of the charging circuit by taking readings with the DMM and the clamp-on ammeter and comparing your readings with specifications. When measuring the charging voltage with a DMM, place the probes on the battery posts. For a 24-volt system, the charging voltage with the engine running above low idle should read 27.5 plus or minus 1.0 volts, or 28.0 plus or minus 1.0 volts for systems conforming to 1991 standards. To test the alternator output current, crank the engine for 30 seconds with the fuel off. Wait 2 minutes, then crank for another 30 seconds with the fuel off. Then start the engine and measure the initial output current of the alternator at high idle. The charging current should meet the spec for the alternator. Finally, observe the DMM and clamp-on ammeter while running the engine at high idle for about 10 minutes. The charging current should taper off to 10 amperes or less, and the output voltage should be as listed below. For 12-volt systems, 14.0 plus or minus 0.5 volt. For 24-volt systems, 27.5 plus or minus 1.0 volt, or 28.0 plus or minus 1.0 volt, 1991 standards. In addition to knowing how to test the alternator, it is important to know about the alternator warning on the electronic monitoring system, EMS. The EMS monitors charging system operation by sensing the output of the R terminal of the alternator. This output is sampled from one phase of the alternator output and reflects both level and frequency. The voltage at the alternator R terminal is a square wave. The base of the wave is at 0 volts and the peak is at the alternator output voltage. This square wave has a 50% duty cycle, meaning that the flat part of the wave spends half the time at output voltage and the other half at 0 volts. As a result, a DMM on a DC voltage setting placed at terminal R will read 50% of output voltage. For example, if alternator output voltage is 28.0 volts DC, voltage at terminal R will average 14.0 volts DC. The output frequency at terminal R in cycles per second, or hertz, depends on the number of alternator poles and RPM. Caterpillar alternators use 12, 14, or 16 poles, depending on the expected electrical load. Their pulleys all turn at 2.3 times the engine speed. R terminal output frequency can thus be calculated for all models as follows. Frequency, Hertz, equals alternator RPM multiplied by the number of poles divided by 120. For example, when engine RPM equals 600, the frequency of the R terminal output of a 12-pole alternator is frequency equals 600 times 2.3 times 12 divided by 120 equals 138 Hertz. If the frequency at terminal R falls below 94 Hertz, the EMS sensing circuit will trigger and the alternator warning LED will illuminate. A square wave of 5 volts average DC is required for EMS to measure the frequency of the signal. However, the normal minimum voltage at R is well above this, being 13.25 volts average DC for a 24-volt system, or 6.75 volts average DC for a 12-volt system. Not every EMS alternator warning is the result of a fault. Some machines have only minimum accessories and need an alternator only to recharge the batteries. Once the batteries are fully charged, the alternator may shut down, causing the EMS to signal an alternator fault. This is not a fault, however. It is normal operation of the machine. When the machine operator sees the EMS alternator warning, a problem usually does exist. The problem may be due to a mechanical failure, slipping or broken drive belt, loose pulley, worn bearings, or an electrical failure, open or shorted starter or field winding, open ground connection, shorted or open diode, voltage regulator failure. When the alternator LED on the EMS panel flashes a warning, you must determine the cause of the warning. Begin by measuring the voltage of the R terminal output and estimating the frequency of the signal. Remember that the signal must be at least 5 volts average to be recognized by the EMS, and at least 94 Hertz to be accepted by the EMS as normal. When measuring the output of the R terminal, it might at first seem correct to use an AC setting on the DMM. But these AC settings are calibrated for sine waves, not square waves. Instead, use the DC volts setting on the DMM to measure R terminal output. The DC ranges read average voltage. With a 50% duty cycle signal, this gives exactly half the system voltage. If the voltage measured at terminal R equals half the output voltage and the alternator is turning without mechanical slippage, the alternator is probably within specifications, at least as far as the EMS is able to determine. The problem may be in the EMS itself. You should also be aware that some alternator failures do not result in an EMS warning. For example, a failure in one of the 2 phases not sampled for terminal R could limit total output current and not affect the voltage or waveform at terminal R. The EMS might then continue to show normal alternator status despite the failure. If you suspect an alternator problem but have no EMS warning, normal voltage at terminal R, and no evidence of problems on inspection, then test the alternator for full current output as described previously. If a partial failure of the alternator has occurred, the ammeter will probably read less than the full rated output current. Also remember that unwanted resistances can occur in the charging system as elsewhere. If they do, such resistances will reduce the efficiency of the system. Check to be sure that the voltage drops across switches, contacts, cables, wiring, and connections in the circuit during charging do not exceed the maximum allowed. These are the maximum allowable voltage drops in a 24-volt charging circuit during charging, with the alternator supplying its rated output current and the engine running at rated RPM. The maximum allowable voltage drops for a 12-volt charging circuit are exactly half the values shown here. Upon completion of this topic, you will be able to analyze the corporate Caterpillar charging circuit to the fault identification level. When you have completed this segment, you will be able to identify symptoms of abnormal operation in the corporate Caterpillar charging system, identify typical fault conditions in the corporate Caterpillar charging system, trace the flow of current through the charging circuit with each of the basic faults one at a time, recognize how each of the basic faults is indicated by readings taken with the DMM and clamp-on ammeter. Close observation of the charging system allows you to detect potential problems early and take steps to prevent them. Repair before failure is usually more convenient and less expensive than waiting until failure happens. Damage is usually less severe, and you can pick your time to do the work and avoid having a machine down during working hours. All of the following conditions are possible symptoms of a fault in the charging system: slow or no cranking, dim or no lights, low electrolyte, except maintenance-free, burned, blackened, or corroded connector or other component, alternator breaker faults, alternator, belt, and pulley noises and visual observations, EMS alternator warning LED lighted. Slow or no cranking or dim or no lights may be due to discharged batteries resulting from charging system failure. Possible causes of failure include broken or slipping alternator drive belt, shorted or open rectifier diodes within the alternator, failure of the voltage regulator, shorted or open wires in the alternator field circuit, shorted or open wires in the alternator stator output circuit. Slow or no cranking or dim or no lights due to an alternator failure may also be caused by ground cable missing between starter ground terminal and engine block, open or intermittent open anywhere in charging circuit, high resistance corrosion on battery terminals, for example, loose alternator drive pulley or wrong, oversized pulley installed, batteries not able to accept a charge due to internal failure. Low electrolyte, water acid level in all battery cells, not just one or two, is usually caused by excessive charging voltage above 30.0 volts DC. The water is broken down, hydrolyzed into gaseous oxygen and hydrogen. Overcharging may also cause warping of the battery plates. If adjacent plates touch, the resulting spark could ignite the hydrogen gas formed during charging and cause the battery to explode. Operation at high temperatures and low humidity may contribute to evaporation of electrolyte. This type of loss occurs much more slowly than loss due to overcharging. Mating surfaces in a switch, connector, or connection can develop various problems that interfere with circuit operation. Corroded, burned, blackened, or melted surfaces may result in high resistance, open, or short circuits. Corrosion can be caused by atmospheric conditions, salt, acid mist, dissimilar metals in contact, or caustic chemicals used in cleaning. Burned surfaces may begin as worn spots which develop resistance and heat. More often, arcing or burning results from a transient high voltage which can be due to voltage regulator failure or to load dumping. Load dumping occurs when an alternator is suddenly disconnected from its electrical load while operating. A brief but very high voltage spike over 150 volts results, which can cause permanent damage to system components. Load dumping may be caused by a loose connection or by opening the battery disconnect switch during charging. Damage increases according to the amount of current flowing at the time the interruption occurs. It also increases if the load is inductive, electric motors, solenoids, etc. A tripped, open alternator breaker indicates a fault in the charging circuit. The most probable fault is a short to ground in the alternator or along the alternator output wire. If the breaker will reset, the fault may be intermittent and may recur. Or the fault may have happened when a tool touched both the alternator output wire and ground at the same time. If the breaker will not reset, the condition that caused the breaker to trip probably still exists. Or perhaps the current surge that tripped the breaker also caused damage, and as a result the breaker will not reset. It is possible for a current surge to be so heavy that the circuit breaker becomes welded together in a closed state and can no longer break the circuit. There may or may not be visual evidence of damage, blistering, on the outside of the breaker. Wiring, components, and breaker may be damaged simultaneously. If only the breaker is damaged the first time a short occurs, wiring and components involved will probably be damaged the next time because the circuit breaker no longer offers protection. Fortunately, this type of breaker failure occurs very rarely. Being alert for audible and visual indications may give you early warning of alternator trouble. Some things to look and listen for include loose drive belt or wrong belt, wear and cracks on underside of belt, worn out or dry alternator bearings, loose pulley or wrong pulley, damaged wiring or loose connections, damaged or overheated alternator. The electronic monitoring system, EMS, monitors normal operation of the charging system by sensing the output at the R terminal, 1, of the alternator. When a problem is detected, the number 8 LED on the EMS panel, 2, is lighted. The source of the problem may be either mechanical or electrical. It is also possible, but improbable, that the EMS system itself has failed. To determine the type of problem, measure the voltage at terminal R. The minimum should be 94 Hz and 13.25 volts DC average for a 24-volt system, or 94 Hz and 6.75 volts DC for a 12-volt system. Problems in the Caterpillar charging system may be caused by an open fault, resistance, short, or short to ground in the alternator. The effects of each of these electrical faults can be demonstrated on the same sample charging circuit already used to describe normal operation. An open in this part of the circuit redirects charging current from the engine ground cable, its normal ground path, to an undesirable ground path through the engine main bearings. This leads to damaged bearings and should be avoided. Because it prevents this damage, the engine ground cable is an essential part of the charging circuit. Here, an open in the voltage regulator has turned off the current to the alternator field winding. This completely prevents the alternator from generating any output. An open in the field winding would have the same effect. An open in one phase of the output windings would reduce output current, but the windings of the other two phases would still operate. When the batteries have been charged for at least 10 minutes at high idle, the voltage as read from the alternator output terminal to the ground terminal should be 27.5 plus or minus 1.0 volts DC, or 28.0 plus or minus 1.0 volts DC for systems conforming to 1991 standards. With an open at the regulator preventing the alternator from operating, system voltage drops to battery voltage, 24.8 volts in this case. When the alternator fails, the batteries do not get recharged. As a result, battery charge decreases each time a load is placed on the batteries. Eventually, the batteries become discharged to the point where they cannot crank the engine or operate accessories. An unintended resistance, such as cable terminal corrosion in series with the intended load, batteries and accessories, robs the charging system of power. A voltage drop occurs across the resistance, leaving less voltage for the system. Lower system voltage results in less available power. W equals E times I, because alternator output voltage and current are limited. A resistance that causes a voltage drop greater than 1 volt in a 24-volt system will result in longer battery charging times. It may also prevent the batteries from ever reaching a fully charged state. The resistance may not be all due to one component, but may be the sum of all voltage drops in the circuit. A short in this voltage regulator has caused full field current, 3 or 4 amperes, in the alternator. Because the batteries were fully charged and have high internal resistance, voltage has risen over 30 volts, but charging current is only 15 to 20 amperes. Most of the current goes to hydrolyze battery water, break the water down into gaseous oxygen and hydrogen, which then evaporates. The high voltage is a warning that overcharging of the batteries is occurring. If you observe charging voltage above specification, investigate. If the voltage is over 30, the problem should be remedied immediately to prevent possible damage to the batteries, warped battery plates, internal sparking, explosion, or voltage regulator. A short to ground of 0.3 ohm or less on a 24-volt system between the alternator and the alternator breaker would cause an 80 ampere breaker to trip to protect batteries. Breakers of other ratings would trip at different resistances. The full rated alternator output would be diverted to the short to ground. A short to ground on any wire attached to the battery positive post shorts the batteries, which can supply very high current. Low resistance is defined here as less than 2.0 ohms. A short to ground of less than 0.5 ohms could melt wire and burn insulation. A high resistance, 2.0 ohms or more, short to ground, would increase alternator load and, with the engine off, discharge batteries. When you have completed this segment, you will be able to describe the procedure for discharging the battery prior to testing the alternator output, the procedure for measuring starting current alternator output, the procedure for evaluating battery condition when testing the alternator, the recommended troubleshooting procedure for the corporate Caterpillar charging system. This section describes the Caterpillar charging circuit test procedure. You can use it to determine whether or not a charging system is working correctly, and if not working correctly, what repairs are needed. The charging circuit test measures alternator output voltage and current under specific conditions. There are 5 steps to the charging circuit test. Turn off all electrical accessories. Then, if the batteries are not already low in charge, partially discharge the batteries. Connect the DMM and the clamp-on ammeter to the charging circuit. Start the engine, jump start if necessary. Immediately go to high idle RPM and observe the initial alternator output current and voltage. Run the engine for 10 minutes at high idle while monitoring alternator output voltage and current. Turn on all electrical accessories and observe the charging voltage. Turn off all electrical accessories. Then, if the open circuit voltage of each battery is greater than 12.4 volts, with the fuel off, crank or attempt to crank the engine for 30 seconds. Wait 2 minutes to cool starter. If the engine cranked normally the first 30 seconds, crank the engine a second time for 30 seconds. Let the starter cool for 2 minutes. Set the DMM to 200 volts DC. Connect DMM red lead to alternator positive output terminal. Connect DMM black lead to alternator ground terminal. Set the clamp-on ammeter to DC current and zero the ammeter. Position the ammeter around the alternator output lead at least 6 inches from the alternator to avoid electromagnetic interference from the alternator. Start the engine. Jump start if necessary. Go directly to high idle and immediately observe the initial charging current and voltage. Current should equal full rated output of the alternator for a short time and then begin to decrease. If the batteries are fully charged, the current will increase at high idle. This chart shows current and voltage readings at startup and presents the appropriate response to each reading. Notes on startup test results. The initial output current reading must be taken immediately after engine RPM reaches high idle. Even a few seconds delay may decrease the reading. The output current of the alternator should be within 10% of the minimum rated output current of the alternator at the specified alternator RPM. If there is any doubt that the alternator under test is running at the rated RPM, you can estimate the RPM of the alternator using the rated RPM of the engine and the diameter of the alternator belt pulleys. To make this estimate, divide the crankshaft pulley diameter by the alternator pulley diameter and multiply this by the rated engine RPM. Batteries must be partially discharged per instructions before test, or rated output current may not be achieved. This chart presents examples of typical Caterpillar alternator ratings. The specifications are intended only as examples. Refer to the appropriate manual for the latest specifications. Continue to monitor the alternator output current and voltage while running the engine at high idle RPM for about 10 minutes. Charging current after 10 minutes should be 10 amperes or less, while charging voltage should be within the following limits. This chart presents appropriate responses to various readings after 10 minutes at high idle. Notes on 10 minutes at high idle test results. The 10-minute test period is an estimate of the time needed for the charging current to drop below 10 amperes and the charging voltage to level out. It may not take a full 10 minutes to reach these conditions if the charging system is in top condition. On the other hand, deeply discharged batteries may take longer than 10 minutes for the current and voltage to stabilize. A rising charging voltage that appears to be headed above the spec may indicate a voltage regulator failure and require a longer test period to confirm. Individual system specs may vary depending on voltage regulator tolerance and ambient temperature. Beginning in 1991, Caterpillar began to phase in charging systems with a higher charging voltage, 28.0 plus or minus 1.0 volts, instead of 27.5 plus or minus 1.0 volts. Turn on all the electrical accessories and observe the charging voltage. If the charging voltage remains within spec, the charging system is good. If the charging voltage drops below spec, look for the cause. Possible causes include too many accessories, deeply discharged batteries, a short. In this segment, you will troubleshoot 3 separate charging circuit problems. Questions and instructions will guide you as you work through the problems. Each of the following exercises begins with the description of a problem one of your customers is having with the charging circuit on a Caterpillar machine. The exercises in this topic guide you through the troubleshooting process. For this reason, you will only be able to change the status of the circuit, operate a switch, or take a measurement in this topic when asked. In some steps, you will be asked to open or close the switch or change the status of the circuit, engine running or not running, lamps on or off. When you are asked, the appropriate symbol is active, and you will be able to open or close the switch or change the status of the circuit by selecting it. In other steps of these exercises, you will be asked to use the DMM or the clamp-on ammeter to make a measurement. When you are asked to make a measurement, the appropriate symbol is active, and you will be able to operate the DMM or the clamp-on ammeter by selecting it. You will also be able to get the results of the Caterpillar charging system test in these exercises when asked. Selecting this special test symbol provides the complete results of the test. When appropriate, both the initial voltage and current readings and readings taken after running the engine for 10 minutes at high idle will be provided. Use your knowledge of electricity and your understanding of the Caterpillar charging system to follow the logic of how these problems are being solved. You are now ready to begin the guided troubleshooting practice exercises for the Caterpillar charging circuit. 2 sets of flood lamps burned out in 2 weeks. Battery electrolyte is bubbling out the vent caps. Here is what you discover when you inspect the machine. You look at the batteries and see they are drenched in electrolyte, water acid. The inside of the battery box and the underside of the battery cases are also wet. The batteries are not maintenance-free types. You inspect the batteries for cracks and find none, but electrolyte is low in all cells. The battery posts and connections appear clean and tight.